Welcome to the next lecture in modern database management, where we'll be looking at modeling data in the organization, how to create models and all that jazz. And let's see what we have next. So the learning objectives define the terms such as database management systems or DBMS, transaction processing monitor or TP monitor, OLAP, OLTP, and all that jazz that comes under the lecture. Understand the importance of data modeling, write good names and definitions for entities, relationships, and attributes. Distinguish unary, binary, and ternary relationships. Model different types of attributes, entities, relationships, and cardinalities. Convert many-to-many relationships to associative entities and model time-dependent data using timestamps. So I would suggest to keep some notes handy. This will help you understand how database management systems work. Entity relationship model constructs. Three major things we cover in this: entities, relationships, and attributes. Entity instance could be person, place, object, event, concept, or often corresponds to a row in a table. Entity type is a collection of entities, often corresponds to the table. Whereas relationships instance can be linked between entities corresponding primary key, foreign key, equivalencies in the related tables. Relationship type, category of relationship, link between entity types, and more. And this is significantly important that you must work with the entity relationship models, because this will allow you to create a DBMS which is flexible and persistent while being consistent also. So let's look into a little bit in more depth what are the ER model in a use case form. So the first use case I would like to discuss here is university management system, where the entities are student, course, instructor. Student has attribute student ID as a primary key, name, date of birth, and major. Course has attributes course ID as a primary key, course name, credits. Instructor has attributes instructor ID, which is the primary key, name, and the department. Relationships: student enrolls and instructor teaches. Student enrolls in a course, relationship between student and the course. Attributes are enrollment ID, that is primary key. Student ID, which is foreign key coming in from the student table. Course ID coming from the course table, where course ID is the foreign key here, and the grade is the last relationship. The teaching or teaches is another relationship that is between instructor and the course. Attribute is teaching ID is the primary key. Instructor ID is a foreign key. Course ID is a foreign key, and semester is another feature. This ER model represents a university management system where students enroll in courses taught by instructors. The enrolls relationship captures the enrollment details, including grades, while the teachers relationships captures which instructors teach which course in a given semester. The next is an e-commerce platform. The entities are customer, product, order. Relationships are customer, places an order. Product contains some data, order contains some products. So places and contains are two relationships. Whereas if I tell in a nutshell, the ER model represents the e-commerce platform where customers place orders for products. The places relationship captures which customers have placed which orders, while contains relationship captures the detail of product which or each order, including quantities and all that, is associated. Same applies on hospital management system. That's where patient, doctor, and appointment happens. Patient has an appointment. Doctor has a schedule to see patients. So the relationship is has and schedules. The ER model that I just discussed represents a hospital management system where patients schedule appointments with doctors. The has relationship captures which patients have which appointments, while schedules relationship captures which doctors schedule which appointments. These use cases illustrate how ER model can be used to represent complex relationships and interactions within different domains, providing a clear and structured way to design and manage databases. Hopefully this has given you some decent idea of the ER model. The figure 2.1 is sample ER diagram. You can look into supplier supplies many items, many to many. Supplier sends shipment. Shipment contain items. Customer submits an order. An order contains products, and products have several items. So you can see the entity type and relationship as the key is given below. Cardinalities are mandatory 1, optional 1, mandatory many, optional many. I would suggest you to read the book carefully, which is given for the course reading, because that will allow you to actually understand in more depth. So entity relationship diagrams include rectangles representing entities and lines between the entities representing relationships. Relationships have cardinalities, which can be one to one, one to many, or many to many. In addition, on each side of the relationship, you can specify that it is mandatory or optional. So the entities can be strong, weak, or associative. So the cardinalities, in addition to the cardinalities, relationships also have degrees. A unary degree represents a relationship between entities of the same entity type. A binary degree represents a relationship between entities of two different entity types. A ternary degree represents a relationship between entities of three different entity types. In principle, you can have relationships between any number of entity types. So in terms of degree is n dash a any. So it depends how you're going to utilize this thing. The business rule is a statement that defines or constrains some aspect of the business. It is intended to assert business structure or the control or influence the behavior of the business. Not all business rules are implemented in a database, and it is the responsibility of database analysts to determine which business rules can be expressed through ER models and which cannot. So the business rule can be that we have to sell a certain product to a certain group of people, that say millennials, and Gen Z has no interest in that. Gen X might buy or might not buy that product. So it depends on the customer segmentation that you do, that how you're going to sell a product to a certain set of folks. Business rules apply possibly implicitly in descriptions of business functions, events, policies, units, stakeholders, and other objects. These descriptions can be found in interview notes of individual and group information system requirements, collection sessions, organizational documents, personnel manuals, policies, contracts, marketing brochures, and technical instructions, and other sources rules are identified by asking questions about the who, what, when, where, why, and how of the organizations. Gathering business rules require good interviewing and listening skills. As a database analyst, you will ask questions about the who, what, when, where, why, and how of the organization. You will need to be persistent and in clarifying initial statements of rules, because initial statements may be vague or imprecise. So this is an iterative inquiry process. So again, it can be declarative, precise, atomic, consistent, expressible, distinct, business oriented. I would suggest you to look into more details that how you're conducting an interview to the stakeholders who are involved. How many types of stakeholders are there when we are making our database management systems? There can be direct stakeholders, indirect stakeholders, direct stakeholders, or non-direct stakeholders. So you will be learning about all these stakeholders when the time will pass in this, and we'll head to the next lectures. Now let's see what do we have in our next slide. So data objects must be named and defined before they can be used unambiguously in a model of organizational data. Data names refer to the names of entities, their attributes, and their relationships, which are the data objects. These names should be meaningful to the business interests and operations. In a sense, data names should be self-documenting, which means they should obviously capture the essence of the data object. So a student, course, and instructor are relatable names, and a student has first name, middle name, last name, the street number, the street name, the county, the city, the state, the zip code, and all that jazz. It is always good to have readable, unique names composed, which you can use in terms of repetition if needed. A student can be a teaching assistant, a student can be a research assistant, a student can be a services assistant. So this will allow you to create something that comes out of your DBMS as more comprehensible for the people who are directly or indirectly associated with the system that you're designing for. It is difficult to obtain a universally agreed upon data definition, so you may want to use multiple definitions to cover the various situations, or alternatively use a very general definition that will cover most situations with data definitions. As with most organizational knowledge, the person who controls the meaning of data controls the data. Thus, definition of data is a source of organizational power. So again, this is significant for us to look into what we are working with and how we are working with. Let's look into the entities in more depth. It is important to distinguish an entity instance from an entity type. For example, an entity may be John Doe, a particular person, but the entity type is person. As a concept, when develop ER diagram or entity relationship diagrams, the boxes represent entity types, not entity instances. Although we use the word entity when describing ER diagrams, what we are really talking about is the entity types. So entity instance is a single occurrence of an entity type at a given time. So here we see a distinction between an entity type and entity instance. The entity type is represented in the first two columns of this figure. It includes the names and of the various attributes. Remember what we talked about regarding data names, as well as the types of data. By contrast, the third and fourth column represents two entity instances. These would be actual records or rows in the final database table that implements this type, this entity type. So character is one, character 10, employee number is character 10 or char 10, 642617836. Example instance can be 534100197. Name has char 25 or character 25. Michelle Brady, David Johnson. Address would be character 30 or char 30. 100 Pacific Avenue or 450 Redwood Drive. So you can see that David Johnson and Michelle are living in two different areas, two different cities. So date hired, birth date. So these are the attributes and attribute data types, whereas example instances are an individual's data that is provided to us to work with. So let's move to the next slide. A common mistake people make when they are learning to draw ER diagrams, especially if they are already familiar with data process modeling, such as data flow diagramming, is to confuse data entities with other elements of an overall information system model. A simple rule is to avoid such confusion is that a true data entity will have many possible instances, each of the distinguishing characteristic as well as one or more other descriptive pieces of data. So an entity should be an object that will have many instances in the database. An object that will be composed of multiple attributes, an object that we are trying to model. An entity should not be a user of the database system, an output of the database system, or a report. So this figure illustrates a mistake many novices will make. The treasurer is the user of the system, and the expense report is an output of the system. Neither of these are entities that should be represented in the database or the ER or entity relationship model. The ER model should represent the objects that are of interest to the user and that will be displayed in system output. Most of the basic entity types to identify in an organization are classified as strong entity types. A strong entity type is one that exists independently of other entity types. So sometimes these are called independent entity types. In contrast, a weak entity type is an entity type whose existence depends on some other entity type. So these are sometimes called dependent entity types. So I would suggest you to give a read to strong and versus weak entities and identifying relationships between them, because that will allow you to understand in more depth how this actually works. The figure shows an entity relationship diagram depicting an identifying relationship between an identifying owner, the employee, and a weak entity, the employer's dependent. Note that the dependent's identifier is only a partial identifier. The full identification requires the identifying owner's identifier as well. Also note that double lines that distinguish the weak entity and the identifying relationship is given in this pictorial representation of the relationship identification. So this is a good example. I would suggest you to read about this in more depth. In addition to general guidelines about naming and defining data objects, there are some specific guidelines for naming entity types. These are listed as singular noun, specific to organization, concise or abbreviation. For event entities, the result, not the process. Name consistent for all diagrams. So if we are working for a hospital management system, we should not put movie in there. We should not put actor in there. We should not put director in there. Director of a movie. We rather put doctor, the patient, the administrator, the nurse, and all that jazz. In addition to general guidelines, defining the entity, and X is what it is. Describe unique characteristics of each instance. Explicit about what is and is not that the entity. When an instance is created or destroyed, changes to other entity types, history of that should be kept for us to maintain the record. In naming attributes, we use an initial capital letter followed by lowercase letters. If an attribute name consists of more than one word, we use a space between the words and we start each word with a capital letter, for example, employee name or student home, address. An entity relationship diagram, we represent an attribute by placing its name in the entity it describes. So the classification of attributes again: required versus optional, simple versus composite, single valued versus multi-valued, stored versus derived identifiers. So this figure illustrates the various properties of an entity attributes. Required attributes must have a value, whereas optional attribute could be null. Note that the identifier is always required. So what is required? Must have a value for every entity or relationship instances with which it is associated. A student must have a student ID number. Otherwise, that individual is not the student of the university. If a student has an ID number, then student has a name, an associated address, the city, the state, the zip code, the major, computer science, data science, artificial intelligence. Optional may not have a value for every entity, relationship, instances with which it is associated. Sometimes many attributes are related to each other, such as the elements of an address. In case they can be grouped into a composite attribute. For simplicity, we can refer to the employee address, but if we want more detail, we can break it into street, city, state, and postal code. So this way we have an option to describe the attribute at a macro and a micro level. Note the use of parentheses for encompassing the components of a composite attribute. A multi-valued attribute is not the same as a composite attribute, although the novices may confuse these terms. A composite attribute is one of the that has many parts, such as address composed of street, city, state, and zip. By contrast, multi-valued attribute is one that can have many different values, such as an employee being able to do many things. Note that derived attribute is not one that is physically stored in the database, but rather one that is calculated based on the value of another. The length of time employed or the person's age are classic examples, as they are calculated based on a fixed starting point, date hired, or the birth date. Attributes can be both composite and multi-valued, and even also derived. So these are distinct concepts. Every entity type should have an identifier attribute. No two instances of entity types may have the same value for the identifier attribute. For example, a person, employee, or a student cannot rely on the first and last name to be an identifier, because many people could have the same name. Rather, the identifier should be something like an employee ID, a social security number, or some other absolutely unique value. In the entity relationship model, identifiers, or also known as keys, are used to uniquely identify entities. Let us look into three specific ER model examples. One is uniqueness, other one is minimality, and the last one is stability. It's not the least. Uniqueness criterion is the identifier must uniquely identify each entity instance within the entire entity set. The example could be in an entity set students, the identifier should be student ID. Each student has a unique student ID, so no two students will have the same identifier. Example in ER diagram could be student, student ID, name, and age. Minimality, the criterion is the identifier should be minimal, meaning it should not contain any extraneous attributes that are not necessary for unique identification. Consider an entity set books. While the combination of the title, author, and publication year might uniquely identify each book using a unique ISBN, International Standard Book Number, is more minimal. The example in ER diagram would be books, ISBN, title, author, publication year. And the last not the least is the stability criterion. The identifier should be stable, meaning it should not change over time or due to changes in other attributes. Example in an entity set, employees using employee ID as the identifier is more stable than using employee name, as names can change due to marriage, spelling corrections, but employee ID typically does not. Example in ER diagram would be employee as employee ID, employee name, position, and salary. These criteria help ensure that the identifiers in the ER model effectively serve their purpose of uniquely and consistently representing entity instances. So hope this is helpful for you to understand how it works. Let's go and see what we have next. So in ER diagram, the identifier will be underlined. Note also that required attributes are typically bold-faced, so all identifiers will be bold-faced as well. If an identifier is composite, then all of its components parts are required. So naming attributes, also known as identifiers or labels, play a crucial role in database management systems for several reasons. Firstly, they provide a unique way to reference and access specific data elements within the database. This uniqueness ensures that each piece of data can be accurately identified and retrieved without ambiguity. For instance, in the table containing employee records, the employee ID attributes serves as a unique identifier for each employee, allowing for precise data manipulation and querying. Secondly, name attributes contribute significantly to the organization and structure of the database. They help define the schema, which outlines logical structure of the data. Clear and descriptive attribute names enhance the readability and understandability of the database schema, making it easier for database administrators and users to interact with the system. Well-named attributes also facilitate better communication among team members as they provide a common language for discussing the working with data. Lastly, name attributes are essential for maintaining data integrity and enforcing business rules. They are often used in defining primary keys, foreign keys, and other constraints that ensure the consistency and reliability of the data. For example, the product ID attribute in an order table can be used as a foreign key to reference the product ID in the product table, enforcing referential integrity. This ensures that orders are only placed for valid products, maintaining the accuracy and integrity of the database. In summary, name attributes are vital for the efficient functioning, management, and integrity of DBMS. Hopefully this is helpful for you. Defining attributes is a fundamental aspect of designing and managing a database management system for several important reasons. Firstly, attributes provide a structure needed to store and organize data effectively. They represent the individual characteristics of or properties of the entities within the database. For example, in a customer table, attributes like customer ID, name, email, and phone number define the specific pieces of information that will be stored about each customer. The structure allows for systematic data storage and retrieval, making the database efficient and easy to navigate. Secondly, well-defined attributes are crucial for ensuring data consistency and integrity by specifying the type, format, and constraints of each attribute, such as data type, like integer string, length, and uniqueness. That DBMS can enforce rules and maintain the accuracy and reliability of the data. For instance, defining an email attributes is a unique string with a specific format helps prevent duplicate or inaccurate email addresses for being entered into a database. Lastly, defining the attributes is essential for supporting meaningful data analysis and reporting. Clear and well-defined attributes enable users to query the database effectively, extracting the information they need for decision-making process. For example, a sales analyst can use attributes like sale date, product category, and sale amount to generate reports on sales, trends over time, or by product category. Without properly defined attributes, such analysis would be difficult, if not impossible, to perform accurately. In summary, defining attributes is vital for creating a well-structured, consistent, and usable database that supports the information needs of an organization. Additionally, defining attributes facilitate better communication and collaboration among database users. For administrators and developers, they provide common understanding of the data, making it easier to share, interpret, and use information across different departments or projects. Hopefully this has been helpful. So if we continue learning defining attributes, the state source of values, the attribute state, whether attribute value can change once set, specify whether required or optional, state minimum and maximum number of occurrences allowed, indicate relationships with other attributes like required or optional. A person has a cell phone and might also have a house landline, whereas required would be one phone number and optional would be the second phone number. So let's continue. Modeling relationships. Relationship types versus relationship instances. The relationship type is modeled as lines between entity types. The relationship instances between specific entity instances. Relationship can have attributes. These describe features pertaining to the association between entities in the relationship. Two entities can have more than one type of relationship between them. That's also multiple relationship. Associative entity, combination of relationship and entity. We'll discuss that in a little bit more depth on these, how to be using that in database management systems. This figure illustrates the difference between relationship types and relationship instances. The ER diagram depicts types. It depicts both entity types and relation types. The metadata and the database is modeled based on the entity types. The actual data that goes into the database are instances, both relationships and entity instances. So there are three types of relationships given in this: unary, binary, and ternary. A unary relationship is when an entity has a relationship with itself. Employee and manager. An employee can be a manager of other employees, so an employee can have a manager who is also an employee. Binary relationship is when two different entities have a relationship with each other. Students and courses. Students enroll in courses, so there is a relationship between the student entity and the course entity. Ternary relationship is a relationship when three different entities have a relationship with each other. Students enroll in courses that are taught by teachers. So there is a relationship among student entity, the course entity, and the teacher entity. These examples illustrate how entities can be connected in different ways in a database. So one example of unary relationship would be supervisor subordinate relationship. Another example which exists between employees. An example of binary relationship may be employee working in a department. A ternary relationship may involve a product being shipped by a particular supplier and to a particular warehouse. The cardinality of the relationships are one-to-one. One, each entity is the relationship will have exactly one related entity. One-to-many, an entity on one side of the relationship can have many related entities, but an entity on the other side will have a maximum of one related entity. Many-to-many entities on both sides of the relationship can have many related entities on the other side. So I would suggest you to look into that in a little bit more depth, and I will give you another example. So one-to-one is technically when one record in a table is linked to exactly one record in another table or vice versa. Person and passport. Each person has exactly one passport if you are within one country. Each passport belongs to exactly one person if you belong to a country. Whereas one-to-many would be, one-to-many is technically, the relationship is when one record in table can be linked to many records in another table, but each record in the second table is linked to only one record in the first table. So one author can write many books. Each book is written by only one author. And obviously, many-to-many in a library, the many books goes to many readers. That's another example. Hopefully this is helpful. Although this figure of unary relationship shows only one-to-one and one-to-many cardinalities, it is also possible to have many-to-many unary relationships. For example, consider a person entity with a friend relationship. A particular person can have many friends, and each friend could in turn have other friends. This is different from one-to-many relationship of employees. Although a supervisor could manage many subordinates, typically a subordinate only reports to one supervisor in this case. Here are binary degree relationships with all the different possible cardinalities associated. An employee is assigned a parking space, that is one-to-one. The one-to-many product line contains product. Students register for course, many-to-many. The cardinality of this ternary relationship is many-to-many. In other words, each vendor could supply many parts to many warehouses. Each part could come from many vendors and be housed in many warehouses. Each warehouse could have many parts from many vendors. The dashed line is a way of representing the attributes of the relationships. For a given vendor supplying a given part to a given warehouse, there is shipping mode and a unit cost. Each of these ternary relationship instances could have its own shipping mode and unit cost. In this figure, we see two examples of multi-valued attributes on the left. On the right, we see separate entities with relationships. The top figure shows a simple multi-valued attribute, whereas the bottom figure shows a composite multi-valued attribute. Note that on the right, it is explicit that there are many-to-many relationships. For example, although the left side shows that the course can have many prerequisites, there is nothing explicit showing that a course could itself be a prerequisite of multiple other courses. Similarly, on the left, it is explicitly shown that an employee can have many skills, but it is not explicitly shown that many employees can share the same skill. The figures on the right, however, do make these facts explicit. The right side of each figure is in Microsoft Visio notation given in this pictorial representation. So the minimum cardinality refers to the smallest number of instances that must participate in a relationship. In simple terms, it is the least number of connections that an entity can have with another entity. For example, in a relationship between students and courses, if the minimum cardinality is 1, it means that every student must be enrolled in at least one course. If the minimum cardinality is 0, it means that student can exist without being enrolled in any course. Maximum cardinality refers to the largest number of instances that can participate in a relationship. In simple terms, it is most number of connections that an entity can have with another entity. For example, in a relationship between authors and books, if a maximum cardinality is many, it means that one author can write multiple books. If the maximum cardinality is 1, it means that the author can write only one book. So cardinality constraints the number of instances of one entity that can or must be associated with each instance is of another entity is technically the cardinality constraint. Note the hash mark versus the circle. A hash mark illustrates mandatory cardinalities, whereas a circle represents optional cardinalities. The figure indicates that each patient must have at least one patient history mandatory and could have many more or many. By contrast, each patient history visit record must be associated with exactly one patient. Note that all the other ER diagrams cardinality is represented using something called crow's foot notation. The three prongs on the many side of the relationship is called crow's foot. There are other possible notations for ER diagrams. For example, Microsoft Visio by default shows an arrow from the many side to one side, although you can change it to crow's foot notation as well. The figure shows a binary many-to-many relationship. In this case, one side is mandatory and the other is optional. Here, every project must have at least one employee assigned to it, but it is possible for an employee not to be assigned to any projects. This is a unary one-to-one relationship. According to this, a person could be married to one or no other person. It's just an example. This figure rules out polygamy. Can you see why? How would we be able to allow polygamy in the ER diagram? Answer, make it many-to-many. Dawn and Fred are single, Shirley is married to Alice, and Mac is married to Kathy. That's the relationship explanation coming in from the entity relationship diagrams aspect. Here we see a one-to-many unary relationship between employees. It shows that a given employee may have exactly 0 or 1 supervisor and could supervise any number of other employees or none at all. We also see that two binary relationships between employees and departments. First, each department must have at least one and possibly one employee or possibly many employees. Each employee must work in exactly one department. Also, each department has exactly one employee as a manager, and each employee can manage at most one department or possibly none at all. The figure illustrates that there could be multiple types of relationships between the same two types of entities. Hopefully this is helpful. Again, we see multiple relationships between two entities, this time between professors and courses. That the is qualified relationship is the binary degree and mandatory many-to-many cardinality. A professor must be qualified to teach at least one course, and a course must have at least two qualified professors. This is a fixed lower limit constraint. The other relationship is actually implemented via what is called an associative entity called schedule, which has an identifier attribute called semester. We will shortly talk about associative entities in more detail. This associative entity is implementing a many-to-many relationship between professors and courses, indicating that a particular professor may be scheduled during a particular semester to many courses and vice versa. Here is an example. Let's consider a database for books and authors. A book can have multiple authors, and an author can write multiple books. To handle this many-to-many relationship, an associative entity called book authors is technically created. The book authors table would have included foreign keys, the references, the primary keys, and the books and author tables. This setup enables the database to record which authors have written which books, accommodating the complex relationships between the books and the authors. In retail scenario, consider a database with customers and products entities. A customer can purchase multiple products, and product can be purchased by multiple customers. To capture the many-to-many relationship, an associative entity called purchases can be created. The purchases table would contain foreign keys and reference the primary keys of the customers and products tables, and this design allows the database to track which customers have bought which products, facilitating the management of sales data and customer preferences. In each of these examples, the associative entity plays a crucial role in linking the main entities and representing the many-to-many relationships. Hopefully this is helpful. In Figure A, the date completed attribute pertains specifically to the employee's completion of a course. It is an attribute of a relationship. The relationship simply states that an employee completed a course on a particular date. The completion is represented as a relationship and is not an entity unto itself. In Figure B, the simple relationship has been replaced with the associative entity. A certificate is considered to be an entity unto itself and, in fact, even has a unique identifier attribute. An associative entity is like a relationship with an attribute, but it is also considered to be an entity of its own. Note that many-to-many cardinality between entities in Figure 2-11A has been replaced by two one-to-many relationships with the associative entity. The associative entity is always one on the many side of the relationship it links. One many-to-many relationship has been replaced by two one-to-many relationships. Hopefully this is helpful. In A and C, we see another contrast of using a relationship with attributes versus an associative entity. Here, a unary many-to-many relationship is converted into two one-to-many relationships between the item, entity, and the BOM structure associative entity. Note the effective date is a partial identifier which implies the BOM structure or bill of materials, for example, is a weak entity and with respect to the item. Figure 213 representing a bill of material structure. Unary relationships, especially one-to-many and many-to-many, often depict hierarchies. Bill of materials, or BOM, is one example. Another example is a supervisor relationship between employee entities in Figure 2-21, slide 41. The relationship also depicts a hierarchy, this time of employees. The three relationships are marked by their mandatory or optional constraints. Number one, states that a vendor may or may not supply parts to warehouse. The number two states that each part must come from a vendor and go to a warehouse. Number three says a warehouse must have at least one part from a vendor. It is recommended that ternary relationships with attributes to be converted into associative entities, although the Figure 2-12C, slide 35 works to depict the general ternary relationships. It is insufficient for depicting the mandatory and optional cardinalities as we see here. Timestamps are useful for keeping historical data. In this case, we see the way of keeping track of price changes over time for products. Can you think of how the price history could be represented as a separate entity instead of multi-valued attribute? What would be the cardinality of the relationship between product and price history? So I would suggest you to answer in the chat, and I will give you a pause here. Hopefully you have written the answer when I asked you to type in the chat on the slide 48. If not, I'm giving you a pause here of 30 seconds, and I will start speaking after 30 seconds to give the answer to the previous slide. So if you are paying attention, that's a good idea, then you can answer that. There are no right or wrong answers. I want to understand if you understood the nature of the entity relationship model. So I'm waiting for next 30 seconds. Please make sure not to unmute yourself. This is rather a chat participation from all the participants. All right, now let's go to the next slide. Once again, the copyright. This work is protected by the United States copyright law, so please make sure that you use it wisely for yourself only, for the educational needs, and do not share this outside of the university domain. Happy learning. Let's continue after a few minutes break. Let's take a 5-minute